Hi, I'm Val, and this is the Geostatistics lecture in the GIS course taught in Linköping University. I will start sharing the screen with my web page. So here on my web page, you have all the courses that I teach, and we will be going into this web page of the GIS course. Here is how it looks like. There are quite a few lecture slides, and for some of the lectures I already have the videos, and right now I will be teaching from this set of slides, Geostatistics. And when I'm done, I will post the video, the link to the video under this set of slides. So geostatistics is statistics when we are taking into account the spatial distribution of the points. Before we go into the subject, let me do a really quick recap of probability. So those of you who took other courses with me, for instance, the airlines management course, may remember that this probability recap, we have a special lecture devoted to it. There is also a video on that linked from the course webpage. So here I have several links to several videos by Arthur Benjamin, in particular his talk, TED talk on probability, which basically is an elevator pitch talk for why you should learn probability. If you don't think that learning probability is a good idea, you can listen to Art. Anyway, so the important things that you need to know about probability is, well, first and foremost, the cumulative distribution function for a random variable y. The cumulative distribution function of the argument k is the probability that y is at most k. Probability density function for continuous random variable, the probability density function is the function such that when you integrate it from a to b, it gives you the probability that the random variable is in the interval ab. For a discrete random variable, we know the probability mass function, which gives you the probability that the random variable attains certain value. So these are the distribution functions. Now, two quantities associated with any random variable are the expected value. Well, here is the definition, so formulas for it, and the variance. Again, here is the definition and the formula for it. So that's more or less all you need to know for a single random variable. Now, if you have more than one random variable, they have a joint probability distribution. Here is what it is. You can define the covariance for two random variables. This is how it is defined. This is the formula for the covariance. And sometimes we'll be denoting the covariance as the variance between x and y, slightly abusing the notation. So anyway, these are some facts that you'd rather know in order to understand this lecture. If you don't know them, you can go to a probability course and refresh your memory. So today our particular interest will be in the random field. So random field is like a collection of random variables, but like a really, really large collection. It's really a collection indexed by all points in R2, all points in the plane. So if you recall what a random variable is, well, a random variable is neither random nor variable, as you may know. It's really a function from the space of events to, well, somewhere else, for instance, to real numbers. But people very rarely really denote the random variable as a function explicitly mentioned in its argument. They just simply denote it like this with some letter. Now, a random field is also a function. It's a function from the event space and the Cartesian product of the event space with the plane. So for any point in the plane and any event in the random space, it outputs a number. So again, we almost never explicitly specify this argument, which is the event in the event space, we usually say that a random field is a random variable indexed by a point in the plane. So essentially, yes, a random field is like a really large vector of random variables. Well, it has infinitely many dimensions. It's indexed by all the points in the plane, or essentially it has a component per every point in the plane, or again, it's like a random variable for every point in the plane. So that's a random field. You know, you have your plane, maybe this is part of the plane r squared, and at every point you have a random variable. You know, it attains some value. And I mean, the examples abound. It could be, you know, the temperature, humidity, how productive certain part of the soil is, anything related to geostatistics, to some geographical distribution. So lots and lots of measurements, lots and lots of variables at every point, a measurement per point in the plane. Okay. And well, we usually don't know the random field at every point in the plane. Instead, what we are given is a finite set of samples, measurements of the data at points P1 through Pn. And these values are, you know, some numbers, Z1 through Zn. Now, if these random variables at different points in the plane were completely independent, then, well, we could study each of them separately from all the others. Then that wouldn't be kind of the topic in GIS. What we're really interested in is the spatial correlation between the random variables. So the variables that are kind of close to each other, they are correlated. They tend to be similar. Like, you know, like if there is a temperature, then maybe, you know, in this region, the temperature is high and then it cools down. So in this region, the temperature is cold. So if you have certain temperature here, then you may expect that the temperature in the close vicinity will be close to the temperature here. But the farther away you go, the correlation drops down and eventually, drops down to zero. The temperature places that are too far away from each other may be completely uncorrelated or independent. So what we're really interested in is learning how the spatial correlation between the random variables may help us with understanding the random field. But anyway, the generic setup is that we have a random field, and that's really a random variable at every point in the plane. So when we do estimation, or as it is more fashionable to say now, prediction in a random field, what we want to do is maybe we have measurements at the various points in the plane, but we really want to know the random variable at a certain fixed point, let's say at the origin. So we know the measurements at all these points, P1 through Pn, but then here is the origin, 0, and we want to know what the random variable is here like. Of course, we will never know what it is really, so we want to create some model for it, Z0. And what do we want to know about Z of 0, or what kind of model do we want to have for it? Well, we may be interested in the expected value of this random variable at 0, but this is not so much of interest in geostatistics. This is more a question of regression. In the regression, you study a lot what would be the average value of the variable at different places, or the function of the independent variables. So what we are interested in is in having a prediction with small variance. So we don't want to have the prediction that tells you, the temperature at certain point can be between -40 and +40. We want to have the prediction with smaller variances. And well, the interesting thing is that we really want to take into account all these measurements taken at other places. In particular, if the measurements are taken at different places, our model for Z0 may change. So we want to take into account the spatial correlation or geography of the measurements. So again, the geostatistics is not so much about all these values that were measured at different points. These values are only used to define the matrix of covariances. We will see it in a minute. but it is very much about the locations, the geography of the measured data. Okay, so one simplifying assumption that we can make, and it's kind of the extension of this idea that we don't really care what the expected value of z of 0 is for our model z0, is that we assume that the expected value of our random field is the same at every point in the plane. Okay, so anywhere in the plane, you can have some average temperature or something like that. If this is not really true, if the temperature has a trend, like going from on the average -10 to maybe 10 over here, well, you can subtract the trend from your measurements and again assume that your random field is stationary, that its expected value is the same, its mean is the same anywhere in the plane. And the specific technique that we will be studying for modeling the variable at a given point is the so-called kriging. There are several versions of kriging. We will be studying the so-called simple kriging, when it is not only assumed that the field is stationary, that is, the mean value of the field is the same everywhere, it is actually assumed that we know what this value is. And we will assume that this value is actually 0. Okay, so we have a random variable whose mean is 0 everywhere. And we want to have a model for the distribution of this random variable at a certain point at the origin. So that's simple kriging, when not only that we assume that the field is stationary, we also assume that we know what the expectation of the random measurement is at any point. There's also ordinary kriging. It also assumes stationary field, but we don't know what this constant is. We only know that it's a constant. And in fact, ordinary kriging is a simple extension of the simple kriging, no pun intended. If you know how to deal with this case, with the case of known expected value, you can also figure out what that expected value is, even if you don't know that. So that's called ordinary kriging. And then there is the kriging with trend, or, well, there are also other names for this technique. It's quite complicated, and we will not study it in this lecture, or actually in this course. Okay, so the central thing, the central notion in the study of isotropic fields is its variogram. So what is the variogram? So we want to know, as we discussed, the spatial correlation or the covariance between the random variables at points P and Q. And in general, well, it's really hard to know what this covariance is, especially if we are only given a finite sample of the data. So we have some complex random field, and, well, we are given a finite sample. Well, how much can we know about it? So we would need to do to make yet another simplifying assumption. So we will assume that this covariance between the random variables measured at points P and Q depends only on the distance between the points. So no matter where you have the measurement, this is your P and this is your Q, and you have the same distance between our points P prime and Q prime, then the covariance between Z of P and Z of Q is the same as the covariance between Z of P prime and Z of Q prime. So the only thing on which the covariance, the correlation between two measurements depends is the distance between them. Okay. In particular, if the distance between 2 points is h, then the covariance between, well, the random variables measured at them is the same as the covariance between z0 and z of h, and we just denote it by c of h. So c of h will be the covariance between the random variables that represent measurements at points separated by distance h, no matter where those 2 points are. In particular, well, C of 0 is the expected value of z squared. Why? Because remember the assumption that expected value of z is 0. So the covariance of z of 0 and z of 0 is just the expected value of z squared. And that's really the variance of z. And well, it's independent of the point in which you look at the random variable, and just denoted by sigma squared. So just the variance of our random variable. Sometimes actually, well, you can see that there is so-called nugget, which tells you that as soon as you step slightly to the right of 0, well, the covariance has a jump, but we will not go into these details. I'll just mention this word nugget, which you may see at other texts or lectures on Kriging. That's what it is. Okay, and the notion, yes, as I said, the central notion for Kriging is the so-called variogram or semi-variogram. So here is the definition. A variogram is a function of a single argument of h, of the distance between 2 points, and this is the variance of the difference between the measurements at a certain point p and p plus h. So if you move p by distance h, then the variance of the difference between these two, well, divided by 2, is the semi-variogram. So it's called semi-variogram sometimes because you divide it by 2, and you divide by 2 just for convenience to have that this g of h is just c of 0 minus c of h. Okay, so let's look really at this expression for. So recall that the variance of any random variable is the expected value of its squared minus its expected value squared. And let's look at the variance of this thing. So the expected value of z is 0. You remember we are in the simple Kriging case, and moreover we're assuming that the expected value of z is 0. So in particular, the expected value of this difference is 0. So essentially the variance, this thing, is just the expected value of the square of z of h minus z of 0. So I'm using 0 in place of p here because, well, we know that we know the simplifying assumption that the variance only depends on the distance between the points. So we're looking at the expected value of this thing squared. Now, what is this? So it's by linearity of expectation. This is expected value of z of h, of z squared of h, which is just the z squared, plus the expected value of z squared of 0. This is again the same thing, and minus 2 times expected value of z of h times z of 0. Okay, and now what are these? How can we simplify this? Remember that we also have to divide by 2. So essentially this is expected value of z squared plus expected value of z squared divided by 2. We just have the expected value of z squared. And then we have 2 times the expected value of this product. Well, here it is. And since the expected value of z is 0, expected value of z squared is really the variance of z. And remember the variance of z, here it is, was denoted by c of 0. And this thing, the expected value of z of 0 times z of h, is really the covariance between z of 0 and z of h. Why? Again, because the expected value of z is 0, and you remember the covariance definition, the covariance between x and y is the expected value of x minus expected value of x times y minus expected value of y. And since in our case, the expected value of z and z of h are both equal to 0, the covariance of x and y is just the covariance of the product of the two variables. So this is just the covariance between z of 0 and z of h, which was denoted by c of h. Okay, so this semi-variogram with all the notation that we have introduced is just the c of 0 minus c of h. Okay, that's the g. And well, here is how the graph of the variogram may go. Well, here it is. You know, the covariance, as we discussed, it may be something large in the beginning, but then as the distance grows, the covariance drops and eventually becomes 0 after some point. So C0 minus C of H, the semi-variogram, it actually starts at 0 and grows because it is C0 minus C of H. And C of H is getting smaller and smaller, so G is getting larger and larger. Okay, so this is the variogram or semi-variogram of a random field. Now, semi-variogram is a nice thing. The question is, how do we know what it is? So we want to estimate, you know, this correlation between the variables at 0 and at h. Well, it would be nice to estimate it from the data, from the measurements. We would just take the square difference of the variables at distance h. Well, here is something that could be the formula for the semi-variogram. So for all points that are at distance h from each other, well, we would take the square difference between the measurements at these points and divide that by the number of such points. But of course, in practice, we don't have the measurements at all possible points in the plane that are distance h from each other. So we look at whatever points we have. You know, maybe these are the data points that we have, or the places in which we have the data points. You know, maybe these two are approximately distance h, these two, and these two, and these two, and so on. So we look at, you know, as many points at distance approximately h as possible, or as many pairs of points at distance, well, approximately h, and estimating the square difference of the measurements between them, dividing that by the number of such pairs, and that's our estimation of the semi-variogram, something called the empirical or experimental variogram. So again, for many, many pairs of points at different distances, you know, h, we get these estimations of the variogram. And then, well, there are some standard assumptions of how the variogram should look like. And then we are trying to fit one of these functions into these data points, where these are not the original data points, but rather these square differences between the measurements taken at different points for as many values of h as possible. Okay, how to do that exactly is, well, really separate research. We are not touching on it too much. That's the general idea. You look at points in your data which are approximate at distance h for various values of h, and then estimating the square difference of the measurements to get the semi-variogram. Now, the interesting thing is that in kriging, this is the only place where you are using the values of the data, you know, the measurements that you've taken at different points, the z values. So you're doing it to estimate the variogram and hence to estimate the covariances. But when we will be modeling, when we will get into our main question to get a model for z0 as a function of all the variables at places of other measurements, we will not be using the values, the z's. We will be only using the p's, the, you know, the P1 through Pn, the points at which the measurements were taken. Okay, so assuming that we know the covariance matrix from all this business, from estimating the empirical semi-variogram, let's now look at what we can do in terms of getting a good model for Z of 0, for the random variable representing our random field at the origin, point 0. So what do we want? So what we want is something that, well, at my times used to be called BLUP, Best Linear Unbiased Estimator. And these days I see it's called Best Linear Unbiased Predictor. Well, because people don't want to estimate things anymore. Everybody wants to predict, right? I mean, you don't want to estimate, you know, the oil price. You want to predict what the oil price is, whatever. I guess that's just a selling point. And I think that BLUP sounds much better than BLUP or whatever BLUP this is. Anyway, what do all these, whether it's predictor or estimator, doesn't matter. What does it mean to be best, linear, and unbiased? Now, best means that you want to minimize the variance of the prediction or of the estimation. So you kind of want to have the low error. So remember, Z0, Z of 0 is the kind of true random variable, the one that you're estimating. This is your model for it. And you want your model to be not very much different from the original variable, or not much different, meaning that you want to minimize the variance of this difference. Okay, in this sense, your estimator or your predictor should be the best with minimum variance. Now, L stands for linear. You want the predictor to be linear, or in other words, you want Z0 to be just the weighted sum of ZIs, where ZIs are these variables at the places where you have measurements. So the real question is really to estimate these weights. With what weights should we take into account, you know, these different estimation points. So here are the points where the estimations were made, and maybe this is your point 0, in which you want to, for which you want to create the model, so that you're interested in Z of 0. And well, you know, some of the points, some of the measurements are very close to 0, and some of the measurements are very far from 0. So it might not be a good idea to, you know, just take the average of all these weights, take Wi all equal. The points that are closer to 0 should probably be given more weight than the points that are farther from 0. And this is the essence of the Kriging. This is the essence of the geostatistics. This is the idea of taking the spatial correlation and spatial distribution into account. How do these weights depend on the locations Pi of all these measurements? But still, so we should be finding the weights, but when the weights are found, then our model should be just a linear combination of ZIs. So that's what linear means, or L. We want our estimator to be unbiased, meaning that the expected value of your model should be the same as the expected value of Z0. And well, I mean, in simple Kriging, we have it for free, because, well, we assume that the expected value of Z0 is 0, and the expected value of all these things are 0. So, I mean, the expected value of the sum is also 0, so you kind of get it for free. If you have the ordinary Kriging, where you don't know what the expected value of Z is, it's a really simple extension to make sure that the linear combination has the same expected value as all these ZIs. Well, maybe you already can guess what is the condition for the weights that should be satisfied. But anyway, now we are doing simple Kriging, so we have the unbiasedness for free. So we are getting this BLUP or BLUP. Best, linear, certainly unbiased estimator or predictor. Okay, now how do we get it? Well, let's see. Let's just write the variance of Z minus Z0, you know, the thing that we want to minimize. Let's just write it out. Here is what it is. The variance, as we know, is the difference between the square, the expected value of the square of the random variable, and the expected value squared. I will write. So, I'm just repeating myself that the variance of a random variable is the expected value of its squared minus the expected value squared. So if we want to take the variance of this, well, the expected value of this is 0, the expected value of this is 0, so the expected value of the difference is 0. So really the variance of this thing is just the expected value of the square of it. Well, here it is. Now, if you write out this square, then, well, you have the double summation over Wi and Wj of the covariance between Zi and Zj. Again, why is it the covariance? Same thing. So the covariance, as you remember, between x and y is the expected value of x minus expected of x times y minus expected of y. But since here we are dealing with random variables whose expected values are zeros, the covariance is just the expected value of the product. So here it is, the expected value of the product, Zi times Zj is the covariance. Then you have the expected value of Z0 squared, and that's just the sigma squared, the variance of our variable. And then you have all these cross products. So Wi's times the, well, expected value of Z0 times Zi, which is really the covariance between Z0 and Zi. Okay, so this whole thing is just this square written out, expected value of the square written out. And remember that we want to find the weights that minimize this thing, minimize the variance. How do we minimize the variance? Well, we set the partial derivatives of this thing with respect to the weights. We set the partial derivative to 0. And what will be the partial derivative of this whole thing with respect to Wi? Well, let's see. When you differentiate this, you have the sum of Wj's times the covariance of Zi, Zj. Here it is. And when you differentiate this with respect to Wi, you get the covariance between Z0 and Zi. And we can define this vector C, where the ith component will be the covariance between Z0 and Zi. So it would have n components, and the first component is covariance between Z0 and Z1, and so on. The last component is the covariance between Z0 and Zn. And so then the partial derivative of this with respect to Wi, well, divided by half, so we are dividing by 1/2, is just the ith component of this vector. Okay. And well, this vector is really something that we already have, because we know the distances between the point 0 and point 1. We know that this covariance is just C of the length of this vector from 0 to P1, or the absolute value of P1. And this is just the C of Pn, of the length of the vector Pn, right? So we have the point 0 and every point Pi where we have the measurement, and we know the length of this thing, denoted like this, length of Pi, and we know that the covariance between these two variables is just C of this length. Okay, and again, once again, we are going from random variables to distances. So we're talking about random variables, but we're really taking into account the distances between the measurement points. Okay, so altogether, we have that 0, the partial derivative of this thing that we are trying to minimize with respect to Wi is equal to that. And we can write it in matrix notation like this. Okay, so for every I, we have Ci in the right-hand side, right? Because 0 is equal to this minus that. So if we, move Ci to the other side, then we'll have that Ci is equal to this summation. Now, what is this summation? So if you have the matrix C, the matrix of all these covariances, so the matrix of all these covariances is C, and then you multiplying the ith row of this matrix by the column vector of weights, the vector of W's, then you get this vector of, covariances between Z0 and the measurements. So for ith row of C, if you multiply it by W, you should get ith row of this vector, or just Ci. So this equation written in the short form or in the matrix form is just that. Okay, this matrix of covariances times the vector W, the vector of weights that we are looking for, the thought vector, is equal to C, this vector of covariances. And well, we solve this equation for W. W is, well, C inverse times C, well, capital C inverse times C. And when we know what the vector of W's is, we can actually calculate what is the variance of our estimator or predictor. Well, Z0 is what? Is W. So I cleared up the whiteboard slightly. Okay, so the this thing, the variance of Z0 minus Z of 0 is this thing. Now, this double summation can really be written in the matrix form like this. You can verify this. So you're multiplying, well, essentially the row of W's times the matrix times the column of W's plus sigma squared. Well, here it is. And minus 2 times this dot product of Wi and the vector C, the cross product of the weights and the vector C. Here is the vector C of covariances. Okay, so now when we know what W is, so we substitute W into here, and well, the transpose of a product is the product of the transposes taken in the other way, and W is C inverse times C. Now this C and C inverse cancels out, and then again we're substituting this thing in place of W. So what we really have in remaining is sigma squared, and now you see that this thing is the same as this thing, well, because these cancel out, because C is a symmetric matrix, and so on. And eventually the variance of your estimator is sigma squared. Well, of course, there is some sigma squared because the original random variable has some variance, minus this thing. And this is super important. And this is the real thing why we were trying to work with Kriging while we were doing all this. Because the eventual variance of your estimator is smaller than the variance of your original that you originally had for your random variable. So sigma squared is the variance of Z of 0 if you know nothing, if you don't do any Kriging, if you don't take into account all these measurements at other places. But by doing Kriging, by taking into account all these measurements, you were able to decrease the variance to this. So this is really the decrease in the variance. So good, we have an estimation which is, well, as good as possible in terms of the variance, and it actually does decrease the variance from what you had originally. Well, that's simple Kriging for you. Well, just as a minor note, it's interesting that if you take the multivariate normal distribution and, well, n plus 1 random variables, and you look at the distribution of one of them given the values of the others. So you can do the math, you can take the distribution, well, of the joint distribution of the variables. Then you will see that the distribution of one of the variables given all the others will still be normal. And this will be its covariance, which just coincides with the, with the variance. So restart. So this is a single random variable, and this is its variance. It's no longer a covariance, it's a variance of a variable with itself. And its variance is the same as the variance of your estimation obtained with the kriging. So in fact, well, kriging is in a sense a generalization of this fact that if you condition the multivariate normal on all variables but one, then, well, you can decrease the variance of that variable. But the decrease is actually exactly the same as you get in kriging for, well, the general random variable under all these assumptions that we have made. But that's just a fun fact. You won't need to use it in this class, but it's good to know. So, well, finally, some literature. So, yes, a lot of the times, yes, kriging is kind of evolved from this, well, conditioning on multivariate Gaussian distribution. I took some lecture notes, in particular these ones were the ones from which I took a lot of the material. I guess they're short enough and interesting to read. They have the simple kriging, but also ordinary kriging. There is more, and there are also comprehensive books on kriging. So kriging is a very well known technique. Yes, a lot of literature, and is used in a lot of places. I hope you have learned something about kriging today.